All right, last video, the challenge problem. The challenge problem is only a challenge because there's a couple extra things thrown in. It's not that difficult. We have an unknown gas. We don't know the number of moles in this gas. We are given the temperature. We're given the atmospheres. We're given the liters. We already know the constant. So the only thing that's missing, which of course we have to solve for, because we always have to solve for it, is the number of moles. We have temperature. We have volume. We have pressure. So we have our P, we have our V, we have our T. We already know what R is. The only thing we're missing is N. Ignore this for right now. All right, so we have to solve for N. Set up as normal. There's our P, there's our V, there's our N, there's our constant, there's our T. Only difference is, notice we're in atmospheres and we're in liters. Atmosphere liters, or liter atmospheres, as you should actually say it. The volume comes first. Liter atmospheres is actually a totally different constant. So we want to represent that by using a different constant. This case, here's what the constant is. It's 0.820578 liter atmospheres per Kelvin mole. It's different because the last time we used 8.3144 cubic meter pascals per Kelvin mole. And that's because we were using pascals and cubic meters. Now we're using atmospheres in liters. There are two famous constants that you use all the time. It's this one, and then the one we use for the other two problems. I would go ahead and just memorize them. There's a lot to memorize. Okay, and that's probably also your new memorization. Memorize those two. Okay, so it's 1.2 times 2.4. You get 2.88 liter atmospheres. There's our constant times our temperature. The kelvins cancel. You get 201.0416 liter atmosphere per mole. You divide what's left over here from both sides. And the liter atmospheres and liter atmospheres cancel, putting the moles on top. You get 0.14325 moles is equal to our N. And that is before the problem even started. That's just solving for the number of moles that we were not told in the beginning. Now we're told that the liters goes down by 50%. Well, that's just cutting it in half. 2.4 goes to 1.2. 1.2 atmospheres goes up 160%. Don't forget basic math. 160 is a percentage. Just move the decimal over twice to get it as the decimal. It's 1.6. So 1.2 atmospheres times 1.6 gives us the new atmospheres. So if you need to review the percentage of increase and decrease, let me know. So this times 0.5 gives you that. This times 1.6 gives you that. All right. So now these are our new pressure and volume. Plug them in with our moles because the question is asking us what is the new temperature. Well, if we're not told the temperature, we have our new pressure, we have our new volume, we have our new moles. We already know the constant. The thing we're missing is the temperature. So plug them all in and solve for temperature. 1.92 atmospheres times 1.2 liters times our moles that we solved for times the new constant, liter atmospheres, leaving temperature out. Moles times this, cancel out the moles. You get 1.01175 liter atmospheres per Kelvin. 1.92 atmospheres times 1.2 liters becomes 2.304 liter atmospheres. You know what? Actually, I'm going to keep going, but I want to show you something in a second. Okay, divide both sides by the remainder of the constant, and the liter atmospheres cancel, leaving Kelvin on top. You get 195.99 Kelvin. Simplifying it because of sig figs, you get 196 Kelvin is equal to the remaining T. Okay, and that's it. So to review, basically we first solved for our missing value, which was moles, and then we actually solved for the problem with the change in by reapplying it, solving for temperature. Knowing the moles, because the moles from problem to problem doesn't change no matter if the pressure and volume change, no matter if the temperature changes. Okay, so we always use the same moles from problem to problem as long as it's the same material that we're talking about. One more thing, just a little bit of a note. So notice that this went down 50%. This went up 160%. A lot of people would think because our pressure and our volume, which are times together, went up overall. It's went up 160%. This went down 50%. Basically, it looks like it's going up a lot more. That the answer, the temperature 245, to the next problem 196, the temperature should have gone up because the percentages seem like they're going up, going down 50, going up 160. It's going up more, but in reality, it's not. Take a look. 1.2 times 2.4 equals 2.88. You multiply them again, 1.92 times 1.2 gets you 2.304. It actually, when you multiply them, it goes down. If you take a look right here, 2.88, 2.304, it went down. So because this side went down, we already know that this side is going to go down. So you can use that as a tool when you're doing problems. If you know that the change has made one whole side go down, you know that your answer change should also be lower than what you had before. A lot of people would multiply this problem and think that the temperature is going to go up, but in fact, it doesn't. This times this was a number problem. This times this gave you something less. Therefore, if that whole thing becomes less, which is the total value of this side, then the total value of this side should go less. And since our constant doesn't change and the moles don't change, the temperature has to lower. And it did. So I hope that answers your questions. If you have more questions, please let me know. There's a lot of complicated stuff in here. The two different constants that you need to know, how they cancel. Yeah, hope that helped.